Good. So hi, everyone. And thanks a lot, Kysian, for the nice introduction, also for the invitation. It's a real pleasure to be here and to meet many of you. And so yeah, I'll be giving a sort of a Blackboard style talk, so hopefully that'll keep things casual. So feel free to interrupt me at any moment if you have any questions. Yeah. So I'll be talking about some work that I did together with Ashvin Vishwanath a few months ago, which broadly tries to link together various different approaches to quantum spin liquids. And kind of the motivation came from some previous work we had where we tried to show how an experimentally relevant Hamiltonian for Rydberg atom arrays could host a quantum spin liquid ground state. And numerically, we saw that it has a spin liquid ground state, but the current project that I'll be talking about today kind of came from the question of, can we get a deeper understanding of this model? Is there some nearby solvable model? And so this is how we started working in this direction. And to our surprise, we actually found that kind of a very closely related model seems to not just describe the Rydberg Hamiltonian, but actually also other related Hamiltonians, even connecting to the Kitaev model, say, which seems like a very different beast. And yeah, that's what we'll be talking about a bit today. So just to very briefly kind of set the stage, I'll be talking about topological phase of matter. And to be precise, what I'll be talking about are so-called intrinsic topologically ordered phase of matter. So I won't be using any symmetry protection in this talk. So the definition of these kind of phase of matter is that, first of all, we'll be considering ground states of local gapped Hamiltonians, say in a qubit system, on some lattice. And secondly, we want it to be distinct from the trivial phase, by which we mean there is no path of local gapped Hamiltonians that connects our Hamiltonian of interest to some trivial paramagnet. So distinct from the trivial state. So the trivial Hamiltonian with a product state ground state. So in particular, we'll be studying Hamiltonians, say like the toric code or whatever other types of interesting Hamiltonians, which have the property that, if you try to tune to somewhere else in parameter space where you have a simple product state Hamiltonian, that along the path somewhere there has to be a gap closing, right? And if that gap closing is unavoidable, we say that we have topological order. We can use that as our working definition. So it's a bit of an, the definition itself doesn't directly tell you why it should be so interesting, but it turns out that examples of these non-trivial topological phases have a bunch of interesting properties. In particular, the quasi-particle excitations, typically fractionalized, which are so-called anyons with anyon statistics. Say I'm going to be in this talk, I'm going to be discussing two-dimensional systems, two spatial dimensions. So there can be anyonic excitations with generalized statistics. So for example, in the toric code Hamiltonian, which is arguably the simplest type of such an emergent topological phase, there's sometimes called E, M, and F anyons, which just means that there's some emergent gauge theory, and you have electric charges for the gauge theory, fluxes, and then the composite, which is an emergent fermion, even though your fundamental system is completely bosonic. And other interesting properties of these states is that they have long-range entanglement. So they're very quantum. In effect, the definition of long-range entanglement is precisely the definition of topological order, right? It's the fact that you cannot adiabatically connect to the product state is almost a defining property that there's some very rich entanglement structure that you just can't get rid of without going through a quantum critical point set. So, okay, that's kind of the general theory side of things. And these models are super interesting in their own right to investigate, but it's of course also all the more fun if we can make some connection to real life experiments. And so there's different approaches to try to find these kind of exotic states in actual systems. So there's this solid state approach, which largely, in a sense, fueled the topic, right? With the discovery of the fractional quantum Hall effect is still remains one of the most powerful examples of topological order. But there's also various different approaches, say quantum magnets. There it's a bit harder to get, kind of completely uncontroversial evidence, but there seems to be a lot of very rich quantum magnets that seem to potentially host such behavior. And there's, the research continues to go in this direction. Okay, but there's also in recent years another possible direction one can explore, which in these more controlled or engineered quantum systems, let me just call them cold atoms in brief. All right, and this contains a lot of different approaches, which I won't try to review. I'll just mention the one that's kind of conceptually relevant for the current talk, which is something called Rydberg atom tweezer arrays. So there's a variety of labs that are kind of developing this technology where they can now even go to two-dimensional systems. So what they do is they say have some alkali atoms like rubidium that they trap in optical tweezers. They can put that in kind of arbitrary configurations. And each effective atom, in a way that I won't really explain, is an effective qubit. So it's an effective spin and a half with interactions. So the Hamiltonian is actually very neat and simple. Essentially, it's an Ising Hamiltonian. It's typically written down as a sort of hardcore boson. So you have some two-body diagonal interactions. So that's the occupation numbers here of the hardcore boson. And then we just have some tunable single side terms, like a chemical potential and some transverse fields. Just to mention, the density here is just, you can write, of course, in terms of Pauli operators to make explicit. This is really just a transverse and longitudinal field Ising model. And so, given that this, simple to write down Hamiltonian describes these actual systems, kind of motivates the question, what can such a simple Ising type Hamiltonian actually do, right? For most of the history of Ising model, we associate it to magnetism, say, or sometimes some frustrated magnets. But for example, you could ask a question, can such an Ising model realize kind of a paradigmatic topological phase, such as a toric code phase that I already mentioned? And it turns out, indeed, in some prior work, we argued, based on, partly also on numerics, that the ground state of this Hamiltonian, once you put it on the right lattice, indeed hosts such a toric code topological ordered phase of matter. But what I'm going to be talking about today is a result of trying to understand better, why does this work, and is it part of a kind of a bigger model space that connects to other models. Okay, and so in this talk, so let me just give you some flavor of where we're heading. So in this talk, essentially, my goal will be to kind of introduce you to a new model that we cooked up. But it's important to note that it's not just a new model that, not just extra on top of the whole literature of topological models, but rather it's a single model that unifies a bunch of other models you might have heard of or we might care about. So it's a new model which unifies other models, other topological models. Hence, it gives some kind of new potential insight into those models. And so I don't yet want to, give all the details of this model. It's a very relatively simple model, but let's work our way up to it. But I just want to structurally give you some sense. It's essentially very much like this Ising type model that I mentioned already up here. So the model we'll be talking about, it actually has a two-body term, which is entirely diagonal. Okay. You can call it classical if you wish on the on-site basis. So diagonal two-body diagonal interactions, and then it has some single side of diagonal terms, which cause some quantum fluctuations. Of course, I'll be making more precise, what the actual Hamiltonian is, but just want to give you a bit of a flavor to know where we're headed. And so, okay, it'll be a relatively simple Hamiltonian, and one can moreover interpret it. The first piece, this diagonal piece, one can interpret as giving us an emergent Gauss law. So we'll get an emergent gauge theory, particularly an emergent Z2 gauge theory, similar to the toric code Hamiltonian. And then this one side piece will actually give us fluctuations of anyons in this emergent gauge theory. So there are kind of two relatively simple ingredients that will give us some rich physics. Okay, and maybe to also just give you a sketch of the resulting phase diagram of this model that I'll introduce more explicitly later. Okay, what is the resulting physics? And there's some tunable parameters in this model. Okay, so So actually, maybe I should also see if I'm not keeping an eye on the chat in case there's any questions. Feel free to just interrupt me. Sorry. Right. Good. So as a sketch of the phase diagram that we'll be getting, say we'll be roughly exploring 3 tunable directions of this model, having to do with 3 possible choices of this fluctuating or single side term. So what the diagonal piece will do us, it will give us, I already mentioned, will give us an emergent gauge theory, and it turns out. Okay, let me maybe just say that one direction of our model will be kind of recovering this Ising type Hamiltonian that's relevant for Rydberg atom tweezer areas. Okay, so let's call this the Rydberg direction, if you wish. That's kind of tuning an Ising model effectively. And if the fluctuations are small, so basically the direction of this axis will parameterize the amplitude of this term, right? So if the term is very small, we just have a classical type of Hamiltonian in emergent gauge theory, and it turns out this will be a solid. This will be a boring phase of matter. There's not enough fluctuations. Whereas if there's too many fluctuations, we'll get a trivial paramagnet. But there's a sweet spot in between where we'll get a Z2 quantum spin liquid in this model. And to be clear again, this is really just an Ising type Hamiltonian, this particular axis. And this particular axis was explored before. This is in work together with Misha Lukin and Ashvin Vishwanath. This was the work that kind of gave a theory proposal for how a Rydberg experiment could get a Z2 spin liquid. And so we numerically obtained this phase diagram here. But now we have a bigger model. In particular, we'll have an emergent Z2 gauge theory from this Gauss law. And one option is having E anion fluctuations. Sorry, this sounds maybe for the next minute, allow me to just throw a few words out there, and then I'll unpack those words. Okay, so I just want to mention some stuff, and then I'll give you kind of the overview of those known concepts, so no one will get lost. Okay, so what we find if we introduce some E anion fluctuations, which again I'll make precise, we'll actually find an incredibly robust Z2 spin liquid for all values of the parameter, which actually connects to this experimentally relevant Z2 spin liquid of the Rydberg atom tweezer area. Moreover, there's a solvable point here. And it turns out that if these fluctuations are infinitely large, we actually recover a Kitaev model. In this case, we'll recover some type of spin 1 Kitaev model, which is just adiabatically connected to this Rydberg atom tweezer area model.
So you're saying the state of the spin 1 Kitaev model is basically G2 spin liquid?
Okay, good. I should let me put a little asterisk here. It's a Kitaev type model. It turns out for spin 1, there's 2 possible Kitaev type models you can define. And it's actually opposite from, it's not the one that has been studied before. Well, it's actually, it turns out let me just maybe say it. The usual spin 1 Kitaev model is like a spin-spin interaction.
Right.
But for spin 1, you can also consider quadrupole couplings. So
I see.
And it turns out that actually is a very, because the usual spin 1 Kitaev is actually either Z2 or a gapless spin liquid, and it's a bit controversial. I won't commit to this, but it turns out this spin 1 quadrupolar model is actually very close to being a fixed point limit, so it has a very short correlation.
I see.
Yeah. Okay, so that's one direction, and then indeed I would say that's kind of Kitaev type model is kind of the same physics as this Rydberg model, if you wish. And then the last axis introduces a different type of anion fluctuation, where again we'll find a Z2 spin liquid that connects to the one we just mentioned up to some threshold. So here in pink is all Z2 spin liquid up to some threshold, and then we get an even more exotic spin liquid, which is some non-abelian spin liquid. And then finally, if these fluctuations are infinitely large, we get the spin 1/2 Kitaev model. And this is the actual Kitaev. So here it's no asterisk, it's literally the Kitaev model. Okay, so this is a bit, I realize that's a bit much, right? I'm just kind of dumping the various results. I just wanted to mention it so that's the world we'll be exploring. And I don't presume that everyone's familiar with all the things I just mentioned. So actually, I'll take a moment now to very briefly kind of review what is the Kitaev model. In particular, I mentioned there's a solvable model. This turns out to be something called basically an RVB state or a dimer liquid. And also, I'll briefly review what is this and what is this Kitaev model. Safe to say at this point that they're both very well-established kind of paradigms for describing or approaching quantum spin liquids, but they're usually thought of as being very different.
Yeah. Here, time-level symmetry is
good. Thanks for the question.
What is the role of time-level symmetry?
Yeah. So this axis, this third axis, explicitly breaks it. So that's why it's possible to get some. This is actually the same chiral spin liquid that we get if you take a Kitaev model and we add a magnetic field. And it actually turns out that it's in fact it's 1 over that field, so that if my parameter is infinitely large, that field is actually 0, and that's why we recover the usual kind of integrable Kitaev model, which is gapless model.
Basically, in that region, we have a Ising anion topological order, right?
Yeah.
And below that, we have G2 spin liquid. I mean G2 topological order.
Yeah.
So basically, there is a topological transition between 2 distinct topological orders.
Yeah, that's correct.
Okay. That's interesting. Yeah.
Actually, let me, for the connoisseurs, let me actually mention that this axis can be mapped to, some of you might have heard of the Jalkivelson model, which actually has the same type of phases. And it turns out this axis can actually be mapped to that model. For those of you not familiar with that, just ignore what I just said. But for those of you familiar with that model, those things are related.
Okay. I have one more question, actually.
Yeah.
So in your model, in this generalized model, so Gauss law is implemented by spin diagonalized spin interactions. So usually in gauge theory, the Gauss law is Gauss law enters as a constraint, but here we have this law energetically. Is that
correct? That's correct.
Okay. Yeah.
Just maybe not that unusual. Like you could think of the totally code Hamiltonian perhaps, right, as a star term being a similar role. But maybe the unusual thing is that it's only 2-body, right? Usually we might think of as these Gauss laws as being multi-body terms. But here it turns out the 2-body term is enough to get a Gauss law. But yeah, it's emergent. It's only energetically enforced now.
Okay.
Thanks. Okay. So okay, good. So now let me unpack some of these concept dimensions. So we had the Kitaev model, we had the RVB state. Let me briefly review both of those concepts. And we'll see that they're actually very different concepts, but they're nevertheless kind of related in this model. So one very kind of, very important approach to quantum spin liquids, both kind of conceptually, as well as actually turns out experimentally relevant, is the Kitaev model. In particular, it's a spin-and-a-half model defined on the honeycomb model. So I'll keep this brief. I just want to give enough so that those of us not familiar just have enough to follow. So this model kind of traces back to the early 2000s. And so we put spin-and-a-halves on the honeycomb lattice. So on all the vertices of the honeycomb lattice. And we label the 3 different directions. So there's a Z bond, this is just a name. It's an X bond, and this is a Y bond. So we label all the 3 orientations in this way. And then Kitaev kind of introduced an Ising type Hamiltonian with 3 different interactions. So the Z bonds have a ZZ interaction, poly Z. And the X bonds have an XX interaction, and the Y bonds have a YY. And then he just introduced what we now call the Kitaev model. So you just sum over all nearest neighbors. And then depending on the orientation of that bond, we have just the interactions I just mentioned. Okay, and so it looks incredibly simple in terms of, if you compare it to other kind of particularly solvable models. It's a very elegant model. And the particular kind of route towards spin liquid here is that it has what we call exchange frustration, sorry. It's just terminology that refers to the fact that the different terms do not commute, right? The ZZ doesn't commute to the XX on the same side. And it's this term, this non-commuting part that introduced a lot of quantum fluctuations, and it turns out enough quantum fluctuations to actually prevent some classical ordering and instead give rise to a much more exotic and interesting quantum spin liquid. And so then the last thing I just want to say is he actually showed that this model is exactly solvable. So let me just repeat the phase diagram. So actually, you can have a coupling, directionally dependent coupling, Jx, Jy, and Jz. And then if we, of course, the global prefactor is arbitrary. So let's say that the sum of the three is 1. Then there's a nice Kitaev phase diagram. So for example, here, Jz is 1 and the other two are 0. Other guys. And Kitaev obtained the following phase diagram. So here, in parameter space, there's due to spin liquids. So for those of you familiar with Torrico, it's the same phase of matter. Here also, and here also. So SL stands for spin liquid. And then here in the middle, there's a gapless spin liquid. So it's even more exotic in some sense. Gapless spin liquid. Okay, so that's a kind of Kitaev model, and there's a lot to say. And also, I guess many of you are familiar with the fact that people are hunting experimental realizations of this, in particular the iridates, which have these kind of couplings and a bunch of other couplings. So there's a lot of interesting physics to explore in that direction. Okay, so that's a whole field in and of itself, you could say. Now, and we'll see that this actually appears in our particular kind of model. So here's some Kitaev type model, and here's some Kitaev type model. But at the same time, our model will also bring together something that seems to be entirely different, which is called the resonating valence bond state. So just say a few words about that. And in fact, arguably, the RVB state is the first kind of theoretical discovery of a quantum spin liquid. It traces back to Anderson's seminal work in the 70s, kind of 1970s. Anderson proposed this idea, but of course, many people have expanded upon this. So let me not even try to put all the names there. And it works with an entirely different kind of approach. So Kitaev works from this exchange frustration point of view, right, which all relies on the fact that the Hamiltonian terms do not commute. Now the RVB kind of uses a different thing, which we call geometric frustration. For example, consider a spin model on a triangular lattice or something, or something made of triangles. And then there's a well-known fact that, of course, if they want to be antiferromagnetic, this one is up, this one is down. Now this one doesn't know what to do, because no matter what it is, it's going to be frustrated with the other two. Which is again going to introduce fluctuations, but now for a different reason in a sense. And then Anderson realized that if this frustration is large enough, instead of forming a classical Ising type order, the system could form in the ground state something called RVB, or resonating valence bond state. So for example, let's just think of the kagome lattice. Here's a little piece of the kagome. So the fluctuations are strong enough. Instead of ordering, they'll just pair up in singlets. So these red ovals are just single. Let me just try it here. So, but moreover, if the fluctuations are strong enough, they won't just crystallize in any particular singlet covering, but they'll fluctuate around different types of coverings, etc. And it turns out this quantum superposition of all possible singlet coverings actually again forms Torrico topological order, or Z2 spin liquid. So kind of the same physics that appeared here in the Kitaev model, but kind of a very different way of getting. Okay, and this is what I said so far is kind of in line with the original idea of Anderson, and then afterwards, other people like Rockshire and Kibbleston, etc., realized that you actually don't need this oval to be a singlet. It could actually be a hardcore, what we now call a hardcore dimer. Where you just think of this oval itself as a quantum degree of freedom, if you wish. The main difference is that singlet, if you have different singlet coverings, they're not actually orthogonal if you calculate the overlap. By definition, these hardcore diamonds, different coverings are by definition orthogonal. And this was actually a very, even though it seemed like a minimal change, it actually was very useful in writing down solvable models, which helped to kind of solidify the concept of spin liquids in the early days. In particular, Dr. Kevelson, Meusner and Sondi, Misquith, Serban and Pasquet. There's a lot of research in that direction. One nice thing, kind of conceptual interpretation of these RVBs, is that they give you emergent gauge theories. So Kissing was already kind of asking about this emergent gauge theory I mentioned. So here actually is an example. So in these RVBs, we always have exactly one dimer touching every vertex, right? If you pair up all spins and singlets, that's what you get, which you can interpret as a Gauss law, because it means that if you, around every vertex, if you calculate the parity of singlets or dimers, you get always to -1. There's always, the parity is -1. This is saying there's always one sticking out, which you can think of as an emergent Gauss law for Z2 gauge theory. So basically, there's two options: either there's a dimer sticking out or there isn't. And here we have a system where naturally you have such a Gauss law emerging. And then if it sounds a bit contrived, or what's the, what have I done other than just slap some word on something? It kind of nicely emphasizes a particular thing, that if you remove a dimer, right? So, in the original kind of Anderson picture, I guess it would mean that you, break one singlet into a triplet. But if you think of this kind of hardcore picture, you just literally remove a dimer. That's your quantum degree of freedom state. It actually creates two excitations. It creates two fractionalized excitations, because now there's two vertices that are screwed up, if you wish. Right? There's two vertices where no longer there's a dimer touching. And indeed, it gives you what we now call two E-anyons. And if there's enough fluctuations, those can move around separately. And this is what you have a fractional degree of freedom. It's an anion, it's very rich, etc. Even though you just kind of naively only took out one thing, you actually get two things. And that's kind of the hallmark of a topological phase. Okay, so far I've just kind of reviewed two, very important approaches to spin liquids. The second one is actually particularly important to us because it turns out that this approach is realizable experimentally in Rydberg atom arrays. Right, so I already mentioned that it's going to be strapped atoms with an effective Ising model. So it turns out that using this Ising model, you can actually implement this emergent gauge theory and get this RVB physics out. So in particular, so this is work. This is the work I cited up here. So in this earlier work, we pointed out that you can get this Anderson RVB physics by putting Rydberg atoms on the bonds of the kagome lattice. So these black dots are Rydberg atoms, say. Sorry, these are the atoms, like rubidium atoms. By the way, this lattice is called the Ruby lattice, this medial lattice of the kagome. And by using the, right, I mentioned the Hamiltonian up here, by using this diagonal interaction of this Rydberg atom tweezer array, you can encode a repulsive interaction that encodes this dimer interaction. So let me just draw. Suppose that this atom is occupied, if you wish, right? So n equals 1. If the interactions are large enough to cover this disk, which is called the blockade radius, RB, then all the other 6 hardcore bosons are prevented from being occupied. Okay, the interactions are strong enough. But that's exactly kind of a dimer condition, right? Like if I draw this as a dimer, it's exactly saying that the 6 neighboring bonds are not allowed to be occupied. So we use our Rydberg interaction, like our Ising interaction, if you wish, gives the dimer constraint. Good. And then in particular, there's the you can then tune the single side field of the Ising model, which is tunable in the Rydberg Adam Tweezer array, which you can interpret physically as creating these Ianian fluctuations, right? Because what is a spin flip, right? It just creates or destroys a dimer. But I just mentioned that's actually like creating Ianians. So we have these Ianian fluctuations, or monomer fluctuations. And if they're too weak, the dimers crystallize into a solid, which is called a valence bond solid. They're not resonating. If the transverse field is too strong, it completely screws up the emergent dimer constraint. Suppose it's stronger than the actual constraint. So then we get a trivial phase. But there's a sweet spot in between where the fluctuations are just large enough, but not too large, where you indeed exactly get the RVB physics. And it's not a solvable model, so it's not literally this wave function, but it's kind of the same physics of that wave function. And that can kind of, this we had to do with numerics, essentially. But even though the numerics was, quite, how to say, robust or clear, still we were wondering, can we actually connect it to kind of something more canonical or fixed point, like true RVB wave function, equal weight superposition of dimer couplings, say. And that's indeed what we found with our model. And in the attempt of doing that, we actually found a model that not just does that, but also kind of links it to this completely different approach, which is this Kitaev model. Okay. So then with that kind of background, let me actually now, I already kind of vaguely said we're going to introduce a model, right, with this physics. Now let me actually, introduce you to the model, right? Maybe you should briefly pause and see if there's any questions.
Yeah, here, so your E anion fluctuation, can you give us the, so what is this in terms of this readable atom?
Yeah. Good. Let me just write, okay, if I just scroll back up, and give you the Hamiltonian here, right? So we have a two-body interaction. This is fixed by this blockade radius I drew. And then these two guys are tunable. But it's basically only their ratios is kind of physical, right? I mean, no one cares about the global prefactor. So it's exactly tuning G over mu if you wish. So let me just write G over mu.
Okay.
So it's tuning the transverse field. Right? So if the transverse field is very small, then we're dominated by this kind of classical constraint. But if there's not enough fluctuations, it just freezes into a dimer solid. But if you have too many fluctuations, you just completely screw up the dimer helper space and you kind of leave it. Does that answer your question? Or
yeah, thank you.
Any other questions?
I have one question. So in order to realize this G2 spin liquid, do we need a finite radius of two spin interaction or two-body interactions? So finite range is important, or just the nearest neighbor interaction will be sufficient?
Great. It's quite important to have this longer range interaction in terms of you need these 6 guys. Like it's in fact, if you only would say have nearest neighbor, that would be like within a triangle. You would actually get a decoupled system that could easily be a paramagnet. So you wouldn't get a kind of, because what we're trying to get is we use interactions to try to get a kind of non-tensor product Hilbert space, right? Because we start with a tensor product Hilbert space, right? Just a bunch of qubits or hardcore bosons, whatever you want to call it on a lattice. But you want to use a constraint to get an effective low energy Hilbert space that's not factorizable, like a space of all possible dimer coverings. And for that, it's actually quite important that you get this large radius to get this dimer constraint. Yeah,
I see. Okay, thank you.
Yeah, there's some more things to say there because the actual experiment doesn't just stop there. It actually has 1 over R to the 6 interactions. This turn out to be quite annoying in terms of you don't want those to kind of screw up your spin liquid ground state. And it turns out you need to do some maneuvering with your lattice to kind of still find the spin liquid ground state. It's still possible, but it's harder. But it's never, it's there in the experiments. All right. Good. So, the above, I mentioned a few models. The above are unified, as unified in a single model, we can think of it as in a spin 3/2, or I just use spin 3/2 as a synonymous for saying a 4-level system. So there's no SU2 symmetry or anything, just 4-level system, a spin 3/2 Ising type model. On the honeycomb lattice. Okay, so why am I suddenly talking about a 4-level system? It's actually directly related to the discussion that we just had. So the Hilbert space, what we're actually trying to get or trying to describe is an emergent dimer model. Okay, so some kind of Hilbert space that looks like, I'm drawing different dimer coverings. So we actually want to think of it secretly as a system living on a honeycomb lattice, where each side is not a qubit, but a 4-level system. So this is 4 levels, 4 possible levels. Basically, there are different possible kind of occupations of this triangle. So either we have an empty triangle of the kagome, or we have the dimer on one of the 3 orientations. For example, this one will, of course, just be the other triangle. So empty triangle or the dimer. So, ultimately what I'm going to define is just an Ising type model on this lattice with a 4-dimensional qubit. But physically, what those 4 levels are trying to represent are the 4 possible states of a triangle of the kagome lattice. Okay. And so now, by definition, this is a tensor product Hilbert space, but I was just emphasizing the fact that dimer models are not tensor product Hilbert spaces. And indeed, this space has too much, right? So actually, our strategy will be to energetically penalize the states which screw up our Gauss law. So when I penalize, for example, right, if I have this one and this one, that would look like this, right? Now, this doesn't satisfy the dimer constraint. Or I could have this one and this one, right? So that would look something like this, or etc., right? All those guys, these are not dimers, right? Meaning these don't satisfy the dimer constraint of having one and exactly one dimer per vertex of the kagome. So our goal will be to introduce a 2-body term that penalizes those configurations. So at low energy, we have an emergent dimer model on the kagome lattice. And then we'll just introduce some ultra-local fluctuations, which you can physically interpret as anion fluctuations, which will give rise to lots of different physics that I mentioned above. That's kind of the strategy. So let me write down the Hamiltonian. Sorry. So we'll have a 2-body term that's trying to do this penalization that I just mentioned. So it'll be nearest neighbor 2-body term on the honeycomb lattice, and I'll be completely diagonal, where Z is a particular 4-level operator. So it's a bit like let me write it down first. It'll look like an Ising type Hamiltonian. I'll introduce this operator in a moment, but it'll exactly do this energetic penalization I just mentioned, such that if J is positive, then at low energies, we have exactly only dimer coverings left over. And then we introduce some fluctuations, some single-side fluctuations, which suggestively I call X, like the usual kind of sigma X. But again, this will be a 4-body, sorry, not 4-body. This will be a single-side operator on a 4-level system. Okay. And this will be the Hamiltonian. So of course, now I just need to define the operators I used, right?
So this model is defined on the honeycomb lattice, right?
Correct.
Okay.
Yeah. And there'll be some bound dependent. So even though the interactions are all diagonal, there's different diagonal interactions on different bounds. And again, we'll use actually the labeling of Kitaev. So we'll have X bonds, Y bonds, and Z bonds. Okay, so let me introduce this diagonal operator. So since what we wanted to do is to penalize these terms, clearly what it needs to do is somehow detect the absence or presence of a dimer, right? Is that simple? So let me introduce Z for alpha equals Z. So I'll define this action on this 4-level state. Okay, so it will detect whether there's a bond in this along the z-axis here. So I'll just draw it out. So it's diagonal, so it'll take. So if there's a dimer, if there's no dimer on the triangle, or the dimer is on the bottom one, it'll just give the plus sign. Whereas if the dimer is on one of the 2 other legs, it will give a minus sign. Okay, so we can visually represent it. It's kind of useful to have a graphical notation where I define the operator as this. Essentially, right, it's just intersecting 2 of the 3 legs of the triangle and checking, is there a dimer or not? Right here, no, no, yes, yes, right? Okay, it's just a useful graphical notation for this operator. For those of you who don't like graphical notation, they want to be very explicit. The above is just, you can write as a matrix. Let's say, let me use this basis ordering. Then it's 1, -1, -1. Right? Just a matrix, if you prefer those. And of course, this is for the particular orientation. Cutting it this way, naturally, I can define, I won't write it out. You can imagine the definition at this point, right? Either I check dimers along this direction or this direction. Right, so this will be negative if there's a dimer here or here. So the claim is, if I put this here, using the Kitaev labeling of bonds, I will get this emergent dimer constraint. So just as a quick example, okay, let's just, let's think we're on the Z bond of the honeycomb, right? So we'll have Z, C. If I just draw this out in this graphical notation, right? That would look something like this, and I can just maybe close this as a little bubble. This is exactly detecting whether this basically, if this equals -1, which you energetically will get if J is positive, right? Then this will exactly give us a Gauss law. Or, more explicitly, a dimer constraint, dimer term like this will indeed be -1, so that's good. Whereas something that violates it, like an empty thing, or a double thing, will be, not consistent with -1. It will be energetically forbidden. Okay. So with this 2-body definition, if we ignore this term for a moment, the low energy space is exactly all possible dimer colors. Okay. And for the main question then left for what is this X term? Or single site fluctuations. And it turns out we only need to introduce one. Maybe I'll briefly stop here to see if there's a question at this point. What I just said. Okay. Similar to the diagonal definition, we can introduce an off-diagonal operator. So on the Z bond, graphically, it can be like this. Basically, now it acts off-diagonally. So if there was no dimer, it'll create it, and vice versa. So, and if there was a dimer on one of the other 2 bonds, it will toggle where it is. And then Hermitian conjugate. And it turns out one can show, I won't bother you with it, but that this tilde string operator and this dash string operator, they anti-commute when they intersect. So in particular, one can actually show that their endpoints, so string operators of this create M anyons, and string operators of this create E anyons. In particular, indeed, for example, it's kind of clear here If you had a dimer, it removes it, which indeed creates two E anyons here if you only acted on a single side. Okay, so anyway, you can just think of it as a definition. Again, if you prefer matrices, it will also be some matrix like this. And of course, you can do it for all possible bonds. So with that, then maybe. So now we know what is this definition here? This XA are three possible choices. This A can be, say, you can call it Rydberg or Ruby lattice, this Rydberg model I was mentioning before, or it could be E-anion fluctuations or F-anion fluctuations. In particular, you can rewrite this Rydberg model I mentioned above, right? This Ising type model. Sorry, all the way here. You can rewrite, you can just embed it in this dimer model. And what you get is the following single side fluctuation, which you can write out in the above operators if you wish. So here I'm using the graphical notation. So again, the dashed line was the diagonal one, and the squiggly line was the off-diagonal one. This is then the product operator. This is the one where I mentioned the phase diagram before. So I want, just to remind you, there was some solid for low fluctuations, a trivial phase for large fluctuations, and a Z2 spin liquid. So this was the model that was studied before. Of course, now we just embedded it, but we haven't really added to it. But now it becomes part of a bigger space you can explore. In particular, a very natural thing to define is just take this part alone and forget about this. That's how we define the E-anion fluctuating model, where you now have fluctuations of E-anions. And it turns out this simple modification already has immensely rich physics. So when the fluctuations are very small, infinitesimally small, then here we get a solvable dimer liquid. Here, the ground state is exactly that of what Anderson envisioned. This kind of equal weight superposition of dimer coverings in the kagome. If the fluctuating term, just the prefactor for this fluctuation, is negative, then there's a phase transition between a Z2 spin liquid and a trivial phase. But remarkably, if it's positive, then it's a Z2 spin liquid for all possible values of HT, all the way to infinity. And moreover, in infinity, I'm afraid I probably won't have, I'm noticing I'm running out of time, so I might not have time to actually explain why, but the claim is that doing perturbation theory around this limit, you get an effective spin 1 quadrupolar Kitaev model, where it's also Z2 spin liquid. And then the last possible choice is, this is if you have E-anion fluctuations of your immersion gauge theory, but you could also have fermionic fluctuations. Again, these are immersion fermions, because the model is actually bosonic. The definition looks something like this. It's the factor of I is to make it Hermitian. Let's not worry too much about the definition. It's some product of the two operators I defined already. And then, again, this very simple definition, it turns out to be solvable for all possible prefactors HT. It's similar to the Kitaev solution, where you map it to a free fermion model. And now the phase diagram, again, if the fluctuations are small, you get a solvable fixed point limit. So it's a Z2 spin liquid. And then at 1 over square root 3, there's a phase transition into a non-abelian chiral spin liquid. And then using the Majorana solution, you can actually show when HT is infinity, it literally recovers a spin 1/2 Kitaev model. Maybe the thing to point out is the way let me maybe zoom out for a moment, right? Because in the beginning, I emphasized that this RVB physics is related to geometric frustration, whereas Kitaev model is related to this exchange frustration, which seems very different. But the way they're naturally linked together is that the way we got the RVB or dimer physics was by having a diagonal interaction, which embodies geometric frustration. But if in a particular limit, where this is the dominant term, then doing perturbation theory in that limit and projecting your Hamiltonian down in that effective Hilbert space transforms these diagonal interactions to the Kitaev interactions. And it's kind of interesting that the same kind of bond-dependent interactions we needed to enforce a dimer constraint, which were like X, Y, or Z dependent, turns out to become exactly the bond-dependent Kitaev interactions. So originally, I was going to explain to you a bit more about this Ianian fluctuating model and explain why you get a stable spin liquid and a spin on Kitaev model. But I think I'm running out of time, right? So maybe I should just summarize, but then I can stay around later if people have more questions or something. Does that sound good? Yeah. Okay. So. Okay, let me just.
Can I ask one question?
Yeah, please. Yeah.
Yeah. So you introduced this string operator representation for your model. So basically, can we think this object as a string operator that creates monomer, some bigens or spin, in terms of a conventional.
That's exactly correct. That's exactly correct. So if we imagine having a piece of the kagome lattice, right, and we have this dashed operator that I drew, and we end it, then you see that because it's a diagonal operator, it will just introduce phase information. So this will create the Vizon,
right?
Or which you can call it M, anion. Whereas the other one. It's actually quite useful to have a little example. So imagine we have some dimer covering initially. And now imagine we have the squiggly line. Okay. So we start with the state that has a dimer constraint on every side. So let's apply the definition. So this definition tells me I should remove the dimer here. On this one, it tells me to toggle it to the other one. And here, I also toggle it to the other one. I'm just applying this definition better. Each triangle. So now I'm done. And now you see everywhere it satisfies a dimer constraint except where my string ended. We have an E-anion or a monomer if you wish. So it's exactly that. We're creating, these are exactly the E-anion string operators. It's defined as a single-sided.
One more question. So for the bigen string, so the endpoint always ends at a hexagon placket, or it can end at triangle placket?
Yeah, it's a great question. So the way it's defined, it can only end at a hexagon placket.
Okay.
Go through. It turns out the algebraic structure of it ending, like you could of course define an operator that does this, right? Which is only -1 on one of the 4 states. It not to have nice algebraic properties somehow. So it really seems like the right thing to do is maybe another way to think about it is, in general, it's easy to write down a Vizon operator, right? You just measure dimers. It's incredibly straightforward. It's actually really hard to cook up an off-diagonal string operator. Like on most lattices, you cannot. Usually what people do is they have a dimer constraint and they try to find like an alternating sequence of dimers and no dimers to then shift all the dimers by 1 step. But that's kind of a state-dependent operation, right? It's very hard to define an operator that you can just act on any state and it gives you well-defined dimer state. In fact, it's impossible for most lattices. It's only possible for corner-sharing triangular lattices, like kagome or squagome and things like that. And the reason I'm mentioning this as a response to your question is that with this operator, which is very constrained, I don't know another definition that works. If you take this, right, and I multiply all 3 legs, okay, which is like an E-anion going around, you can algebraically show that the product of these operators is 1.
Oh,
which is, there cannot be no vice on there. You see?
I see. I see.
Yeah.
Oh, that's very nice.
Thanks.
Yeah. Actually, one more question. So, can you go to the next page?
Yeah.
So here you introduce 3 different types of X operators. So in the first case, we see, we have 2 combined string operators. One for Bison, one for spinons. So does it correspond to a fermionic spinons or?
Yeah, it's a great question. You can, okay. This is the question. So you can think of it as indeed as okay, what it does do indeed is it creates an E and M pair, right? Like it creates an E here and an M here.
Yes.
So in that sense, you can think of it as creating a fermion. But it turns out that it doesn't so much induce fermionic dynamics because it turns out that the natural fermionic string operator turns out to be something like this, where they intersect. And this has to do, there's like the simple way to think about it is that E anyons and M anyons live on different effective lattices. M anyons live at the center of hexagons and E anyons on vertices. And those lattices have different lengths, so they don't naturally hop in the same direction. Whereas the spacing of the center of the hexagon is twice the spacing of the length of the kagome. If the M anion hops 60 degrees in one direction, whenever the E anion hops, they both move a unit to the left. Okay, that's more kind of an algebraic way to think about it. Maybe a more physically interesting way, it has to do with framing. So if you want to define a canonical notion of F, right, then to each E anion, you have to decide, is my partner M living on the right of me or on the left of me, right? Because for each site on the kagome, like if I'm on this site, right, I have a plaquette here and I have a plaquette here, right? So I have an E here. Am I going to put M here or M here as my canonical fermion pairing, right? That's like a notion of framing. I have to choose it.
I see.
It shows that if you make a choice and then write down a hopping operator for that choice, you get.
Okay.
Yeah, maybe there's an even better way to think about it. I don't know, but it turns out that the natural fermionic model is rather this. Yeah, even though you can kind of think of this as creating, F pairs as well.
Yeah, thank you.
Thanks for the question. Yeah, okay, so thanks a lot for this question.
Can I ask you a question? I read your another paper about generating topological order state by projection or measuring SPT state. And at the beginning of the spin liquidity can be served by gauge system, and there's emergent Gauss constraint. So is it a connection or not? I mean, Gauss law can be interpreted to projection of space without Gauss constraint. So is there any connection?
Can you rephrase the last part? Actually, in Gauss law and so yeah, are you asking the connection between measurement and Gauss law, or what's the?
I mean, Gauss constraint is something we can interpret Gauss law, Gauss constraint as a projection of space without Gauss constraint.
Yeah.
Is there any comment?
Yeah, no, I agree. I think that's a good connection to make. So indeed, in this kind of measurement-based approaches to creating topological states, indeed, what you're trying to do. So in my talk, I'm very much focusing on Gauss law. So what is a Gauss law? Right? It's just a local way of defining a constrained Hilbert space, right? Like you keep track of things and you're enforcing a condition that kills, excludes many states. And the beauty of such constrained Hilbert space is that, right, if you have a constrained Hilbert space and then just have a superposition of all possible states consistent with that constraint, it can have topological order. So it's a very natural route towards topological order. And indeed, you're bringing up kind of a seemingly different approach to creating topological states where people kind of create non-topological states, like a product state, and then they do particular projective measurements. and suddenly end up with toric code or other states. And indeed, you can exactly imagine that measurement as enforcing a constraint. That the measurement is kind of telling, it's kind of indeed measuring the binary, or are you, do you have closed loops or not, something like that. And indeed, that's how it's able to, measurements can enforce a constraint, and hence, if there's enough fluctuations in the remaining part, it will give you topological order. Yeah.
Thank you.
Does that answer your question?
Yeah.
Okay, yeah, so I'm over time, so let me conclude. But yeah, these questions are really good, and also, yeah, Kyusung kind of nicely emphasized some of the key facts, and indeed, so many of these things I wrote down, you can kind of intuitively interpret as like arguably the simplest way you would write down fluctuations consistent in your Hilbert space. But it turns out that in this four-sided Hilbert space, those kind of relatively simple things to write down, like I would say this is the simplest fermionic fluctuation, this is the simplest monomer fluctuation, they give us this very rich, phase diagram that I won't completely repeat, but when I had this E-anion fluctuation, F-anion, and you had like a very broad Z2 spin liquid, which even connected to the Z2 spin liquid in the Rydberg case. So it gives you kind of a new way of approaching someone. Let me just conclude. This kind of relatively simple model gives you some new conceptual connections. In particular, it shows that writing down the minimal, so okay, what is a kind of a lesson, right? Is you try to write down the minimal diagonal interaction to enforce a Gauss law, which in some cases can be two bodies, so not so unphysical. And then instead of then trying to write down many body operators to give you fluctuations, you actually just try to write down the simplest local thing and explore what the consequences of that are. And the reason is maybe slightly counterintuitive is that these local terms, these anion fluctuations, they're kind of the things that screw up your Gauss law, right? Like they create monomers, etc. They kind of create dirt. But it turns out that, sometimes these fluctuations can be, still give you a very stable phase of matter, and a particular link to, say, one experimental connection is to Rydberg arrays. But it also, sorry for the sloppy thing, I'm just trying to wrap up. But another connection is to this Kitaev world, which is up here and here. And it even gives us not just new connections or new insights into experimental systems, but also gives us potentially new experimentally relevant systems. So one thing I didn't have time to discuss, but it's in our paper for those of you interested, is that it gives you some Rydberg or cold-atom related different models that seem to host spin liquids. But the last thing I just want to mention for the solid state also audience amongst you is also the last thing I want to mention actually is sort of question to you. I'm going to ask you a question to the audience. So, one model we found up in here in phase diagram is a simple spin one model, which is the last thing I'll write down. But instead of the Kitaev model, which is a spin-spin interaction, what we found is it has the same features as the Kitaev model that is bond dependent, but it's for a quadrupole operator. So in particular, the Z bond, for example, will have the quadrupole XY term. Just to remind you, quadrupole operator is this operator. And it turns out this simple model, which is like a quadrupole version of the Kitaev model, so spin one, it turns out to have a very robust Z2 spin length. The correlation length is like less than a lattice spacing. We find in numerics. But I don't think I haven't seen them in experimental context. So I just wanted to mention it. And I was kind of if anyone knows a potential experimental relevance for this or related models, let me know. But okay, with that, let me just end here and thank you all for your time and attention.
Wow, it was very nice talk.
Oh, thank you. Yeah, thanks for the great questions.
No problem. It's time for questions. So if you have questions, please unmute yourself and speak. So actually, I have questions, several questions. So you showed the phase diagrams. How did you obtain those phase diagrams?
Great. Yeah. Okay. Yeah, good. Maybe I should mention the rigorous statements are these three phase diagrams, which are the three axes, as well as the fact that we show that they're connected. So in particular, we showed that we numerically showed that this previously observed numerical spin liquid is algebraically connected to this model. We just numerically with DMRG, we showed some kind of path that stays gapped. And this broader phase diagram, the space in between, that should be studied more with numerics. But to answer your question, how do I know this and this, which is that's this axis and this axis? So the last one is easiest. It's solvable. So in particular, okay, you're well familiar with, like, say, Kitaev's method of writing a spin 1/2 as 4 Majorana's. For spin 3/2, you can write as 6 Majorana's. It turns out if you do it for this model, you exactly get, this Kitaev type, conserved fluxes, and you fix the flux sector, you get quadratic Majorana's. So that's how you solve for this. And then lastly, this model. It turns out, originally we started doing this numerically. We found it a spin liquid. But it turns out, actually, you don't even need to do that much work. So it's not solvable, but there's a duality mapping to a known model. In particular, there's a non-local Kramers-Vanier mapping to the transverse field Ising model on the kagome lattice. So the usual spin 1/2 model on the kagome lattice. And people have studied that with Monte Carlo decades ago. And interestingly, in that case, people were disappointed because they found that it's like almost everywhere a paramagnet. But the fun thing about the non-local duality is that what is paramagnet in that language actually is easy to spin like a non-language. So that's kind of how we're quite confident that it's easy to spin like everywhere, because it's people tried hard not to find the paramagnet, and they found it, so they were confident it's easy to spin like a non-language.
So then the spin one, the spin 1 quadrupolar Kitaev model, is it exactly solvable?
Great. I think not. No. It does have conserved plaquette operators, but so does the spin 1 Kitaev model. And that's also not solvable, right, as far as we know. So it has conserved plaquette operators, but not solvable. And maybe just to mention, for those of you interested, in our paper, we wrote down a model that interpolates the spin 1 Kitaev. Actually, there's a natural interpolation from the spin 1 Kitaev quadrupolar model to the spin 1 Kitaev model. But we haven't studied this numerically because there's time in the universe. So, but that could be an interesting thing to explore. But maybe we can give some new insight on the spin 1 Kitaev model, but not solvable as far as I'm aware.
So I have a probably related question. So I want to make sure I understand correctly. So for your phase diagram, so for the generic field direction, so if I interpret this axis as a field, so Ruby H, E, H, M, I don't know. So, and for the generic direction, are you sure the phase diagram or
yeah, that's a good question. No, in the paper, we're more careful to point out that this is a schematic kind of phase diagram. So rigorous things is this axis, and this axis, and we know we've numerically checked that these are connected, and we also know analytically that this axis joins with this axis. So we do know that the spin liquids are connected. The way in which they're precisely connected, no, that's really just schematic. We just know, they are connected in principle because they're the same phase of matter. But yeah, what the precise shape of this phase diagram, we don't know. That should be studied. Yeah.
One more question. So I like this idea a lot. But if I ask a very trivial question, so if I think about this 0 point of your phase diagram, there. The ground state manifold the degeneracy is extensive, I guess.
Oh, good. Yeah. So that's correct. So the literal origin is all possible dimer coverings. But if you do perturbation theory, you get an effective dimer Hamiltonian. Turns out that Hamiltonian in both of these axes, you get the same Hamiltonian. And in both cases, it's a solvable fixed point Hamiltonian. It's like an RK type Hamiltonian in the spin liquid regime. And they're the same. So we know the physics is connected.
Yeah. Thanks.
Thanks.
Is there any other questions? Actually, I have one more question. So, okay, so in the axis of FF fluctuation, the vertical axis. So you mentioned that there is a, G2 topological order near the origin, but away from that point, we have a Ising-Ennion topological order. So that means there must be a topological transition between them.
Mm-hmm.
So can you make a comment about that transition? Is it what kind of signature you see? Yeah.
Yeah, it's a good question. So it's okay. I mean, well, the first point to make is that it's an effective quadratic, so not quadratic, a free fermion band reshaping, right? Because the whole axis is free fermion solvable, and it's all happening in the flux-free sector. So it's in that sense, it's quite similar to the transition in the usual kind of like, imagine taking the Kitaev model with the solvable kind of further range non-abelian spin liquid, right? I don't think that one was not in the original Kitaev paper, but it was later pointed out that you can write down a solvable model for the gapped non-abelian spin liquid. In that model also you can have a direct transition between the non-abelian spin liquid and the Z2 spin liquid. Now, even in that case, I don't directly know what to say, but yeah, there will be some kind of effective free fermion transition. Okay, maybe what I can say, it's an effective P plus IP transition in the free fermion model. So whatever that looks like, like a trivial fermion to P plus IP fermion in a free fermion universe. It'll, whatever the band does in that case, like band closing, opening. Maybe there's more books for it. Maybe one thing to point out is that it's this Z2 is a different SET from these three. So
which
it's a different symmetry enriched topological order. So Z2 and this is Z2, but there's some. I think they're distinct in a subtle way. As with translation symmetry, they're not connected. So there's like some different Z2.
I see. Is it like a double semion G2 topological order?
Oh, no. It's still toric code. So in the absence of translation, they can all be connected.
I see.
But if you enforce translation symmetry, they're just subtle.
It has a different symmetry fractionalization. So that's what you are saying.
Yeah, that's
okay.
Correct.
I see. Is there any other questions? If there is no further questions, let's thank the speaker.
Thank you. Thanks a lot for the fun questions as well.
Yeah. Oh, Ruben, it was very nice talk. I really enjoyed it.
Oh, thank you. That's very nice. I appreciate it.
Yeah, the presentation was very nice. I looked at the paper. It was very long paper, but I like this talk a lot. So now
awesome.
It's easier.
Okay, great. Happy to hear.
I have to run, Ruben. So it was very nice to meet you. And I leave you to discuss more.
Bye. Ciao.
Yeah, people are leaving now.
Yeah. Thanks. Nice meeting you.
Yeah, it was very nice.